Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 4, Lesson 4 on finding equations of exponential functions. In the last lesson we reviewed the basics of exponential functions. In this lesson we're going to see how to find the equation of any exponential function as long as you know 2 points on that function. Let's dive right in and start with a simple exercise. All right, basic equation forming. One of the skills you acquired in Algebra 1 was the ability to write equations of exponential functions if you had information about the starting value and the base, which is the multiplier or the growth constant. Let's review a very basic problem. Exercise number 1. An exponential function of the form f of x equals a times b to the x is presented in the table below. Determine the values of a and b and explain your reasoning. All right, well, what I'd like you to do is pause the video right now, think about what we talked about in the last lesson, and maybe even remember some things from Algebra 1, and see if you can flesh out what the equation of the exponential function is that is represented in this particular table. Well, one of the values that I hope was pretty easy to find was the value of a. We discussed extensively in our last lesson that a is the y-intercept of this function. So a is going to be equal to 5, right? The value of a is always the y-intercept of the function. It's always its value when the input is equal to 0. All right. Now, the value of b, the base, is going to be the number that we're going to multiply a by for a 1 unit increase in x. So we can see, right, that the x's, and this is very, very important, the x's in this table increase by 1 unit each time. That's very important. We're going to get into more complicated exercises where that doesn't happen. When we look at the y values, what we can see is that to go from one y value to the next y value, we are always multiplying by a factor of 3. And that means that b is equal to 3. Our final equation, therefore, is f of x equals 5 times 3 to the x. And really our explanation is what I just went through, right? Which is that a is equal to the y-intercept, which is equal to f of 0, and b is equal to our multiplier per unit increase in x. And again, I have to keep emphasizing that unit increase in x because, you know, if I went from the 5 to the 45, right, the multiplier there would be 9. But the unit increase in, the increase in x from the 5 to the 45 isn't 1, but it's equal to 2, all right? So in Algebra 1, every time you ever came up with the equation of an exponential function, you always had a table where x was going up by 1 unit each time, so all you had to do was look at the y values and say, well, what is the ratio of 15 to 5? Well, that's 3. What is the ratio of 45 to 15? That's 3. 135 to 45, that's 3. So it was easy enough. Now, obviously, we're going to take this to a different level in Algebra 2, so let's get into that right now. More challenging equations. Finding an exponential equation becomes much more challenging if we do not have output values for inputs that are increasing by unit values, increasing by 1 unit at a time. So let's take a look at how we do that. Make sure that you have a graphing calculator handy because we're going to be using that a lot in today's lesson. Exercise number 2. For an exponential function of the form f of x equals a times b to the x, it is known that f of 0 is equal to 8 and f of 3 is equal to 1,000. Letter A. Use the fact that f of 0 is equal to 8 to determine the value of a. Show your thinking. All right, this should be easy enough. Pause the video and let me know what the value of a is. All right, well, maybe I gave you too much of a hint in letter A, but the value of A is equal to 8, right? So again, A is always equal to the x-intercept, which is f of 0, and that happens to be 8. All right, so that's awesome, because to figure out the equation of any exponential function, we just need to know two things. We need to know the starting value, right, the y-intercept A, and we need to know the multiplier b. Now let's take a look at letter B. Use your answer from A and the fact that f of 3 is equal to 1,000 to set up an equation to solve for b. You will solve for b in part C. And I apologize for all the A's, the B's, part C's, part A, part B, etc., right? Now, let's take a look at something. Whenever we have a mathematical model that has parameters like A and B or M and B or what have you, right? If we know one of them, it's wise to substitute it in. So right now, our model is f of x equals 8 times b to the x. So I know my A, it's equal to 8, it's part of the puzzle, I put it in, right? What I don't know is b, but I do know that f of 3 is equal to 1,000. Because of that, what I can now do is I can put in 1,000 for f of x. I still have 8 there. I don't know what b is, but I know that x is 3. Anytime that I know that a particular point like f of 3 or 3 comma 1,000 lies on a particular function or curve, I can always substitute it into that curve because I know it makes it true. And now this is an equation that only contains one variable, right? That variable being the base that we're trying to solve for. So let's take a look at letter C now. Solve for the value of b using properties of exponents. Awesome. Let's do it. And let's do this one together. You're going to do plenty of these today in this lesson, right? So I want to solve for b. The first thing I'm going to do is divide by 8 on both sides. All right. Now, 1,000 divided by 8 is 125. I do want to emphasize something though. If you wanted to, you could leave it as 1,000 divided by 8. All right, your calculator can handle 1,000/8 just fine. Now I want to figure out what the value of b is, and I have two options at this point. I can either take the cubed root of both sides, or I can raise both sides to the 1/3 power, keeping in mind, of course, that the 1/3 power and the cubed root of a number are the same thing, right? So either I can do this, or I can simply use the cubed root function. All right, and actually, let's take a look at both of those on our calculator, right? So if I bring my calculator out, remember, what I'm looking to do in this situation is find 125 to the 1/3. That's, of course, very easy to do. I just type in 125. I use my caret button. If you really want to see it in terms of a fraction, you can just do that and hit enter. That tells me that my base is going to be equal to 5. Or if you prefer the cubed root, and I prefer fractional powers over the roots themselves, only because I think it's a little bit easier, but you could also do second caret, which gives us the general root function. I have to put a 3 there to get a cubed root, and then somehow I have to get over there, put 125 in, and I also get 5. And I'm probably going to emphasize this a little bit as we go through the lesson, because to begin with, it's a great way to just simply review the fact that fractional exponents and roots are the same thing. All right, regardless, b, as we see now, is equal to 5. Let's go back to our full screen, right? Finally, letter D, determine the value of f of 2. Well, in order to figure out what f of 2 is, it may be wise to just write down f of x now, because we have everything. F of x now is equal to 8 times 5 to the x. There's our full exponential function. So now if I want f of 2 is going to simply be 8 times 5 to the second. That's going to be 8 times 25. And that happens to be 200. Of course, you can do that on your calculator if you so choose, but it's easy enough to also do in your head. All right, Now, we're going to see this happening quite a bit, all right, especially taking roots or fractional powers in order to find the value of our base. Let's take a look at another problem, see how much you got this. Exercise number 3. An exponential function of the form f of x equals a times b to the x exists such that f of 0 is equal to 7 and f of 5 is equal to 20. Determine the value of b to the nearest thousandth. Check your answer using f of 5 equals 20. All right, well, this is very similar to what we just did in the last problem, except it's all sort of at once versus broken up into 4 different parts. Pause the video now and see if you can figure out the value of b to the nearest thousandth. All right, well, because we're given f of 0 is equal to 7, right, due to the fact that we know this condition, then immediately what we can say is that f of x is equal to 7 times b to the x. All right, now using this particular condition, we can say that 20 is equal to 7 times b to the 5th. We can now divide by 7 on both sides, and unlike the last problem, where we, had a nice sort of ratio that turned into a whole number, 20/7 isn't particularly nice, so I have b to the 5th equals 20/7. Simple enough. Now what I'm going to do is I'm going to say, well, b to the 5th raised to the 1/5, or to the 5th root, either way, is equal to 20/7 raised to the 1/5. Again, just going back to my calculator really quickly. Eventually I'll stop doing this. But I'm going to do parentheses, go with my fraction, 20/7 raised to the 1/5, and I find that my b is 1.234, which I sort of love to the nearest thousandth. 1.234. And again, just like before, we could certainly, if you like the root button better, you could say, well, it's going to be the 5th root. Whoops, that's not what I want. It's the 5th root of the fraction. So much fun. 20/7. And that will also give us the same thing. Again, it's good to just sort of keep hammering on the idea that the 1/5 power and the 5th root are the same thing, right? Either way, we find that b is equal to 1.234. All right, let me go back. Actually, I'll just stick here. b is 1.234. So in theory, right, our exponential function is f of x equals 7 times 1.234 to the x. Now, granted, they just said find b, right? Now, the last thing that they asked us to do is to check our answer using f of 5 is equal to 20. So let's see what f of 5 is really quick, right? So f of 5 is going to be 7 times 1.234 raised to the 5th. All right, and if I do that, what I get as an output is 20.02, etc., right? And let's go back to the screen really quick so we can see this sort of a little bit larger. 20.0296, etc. Now, it's not exactly 20, all right? And you can probably understand why that is. It's not exactly 20 because we had to round our base, right? We rounded our base to 1.234. That's actually, this number up here is actually an irrational number. So we have to choose to round at some point. But then when we use our model, right, even to just check to see if we're right, we have this little bit of inaccuracy, right? Just a little bit. All right. Let me put that away for right now. And let's go back into our full screen. And let's talk about any two non-vertical points. Just like with lines, any two non-vertically aligned points will uniquely determine the equation of an exponential function. So in the last few examples, we gave you 2 points, but one of them was the y-intercept. That doesn't have to be the case. So let's now take a look at how we do a problem that's the most general out there where you don't have the y-intercept to begin. Exercise number 4. An exponential function of the form y equals a times b to the x passes through the points 2, 36 and 5, 121.5. Letter A. By substituting these 2 points into the general form of the exponential, create a system of equations for the constants a and b. All right, this is really cool. So what I'm going to do is I'm going to take this point and I'm going to substitute it into this equation. All right, now what's that going to look like? Well, 36 is going to go in for y, and 2 is going to go in for x. So all it's going to look like is the following. 36 is equal to a times b to the second. All right, that's just taking that first point and substituting it in. But I want a system of equations because this is just one equation with 2 unknowns, a and b. So now I'm going to take 121.5 and substitute it in for y, and then 5 and substitute it in for x. So 121.5 substituted in for y, and 5 in for x. And now we have a system of 2 equations with 2 unknowns. Generally speaking, as long as the number of equations that you have matches the number of unknowns that you have, you should be able to solve that system for the 2 unknowns. And I know I got a lot of math teachers out there that are screaming at me right now and going, well, that doesn't always work. And totally true, right? You can definitely have a system of equations where you end up having an infinite number of solutions or no solutions whatsoever, and we won't get into that right now. This one we're going to be able to solve. So let's take a look at letter B. Divide these 2 equations to eliminate the constant a. Recall that when dividing 2 like bases, you subtract their exponents. All right, so back when you were working with systems of equations in Algebra 1, you oftentimes used the elimination method, where you would add 2 equations together and have opposite values cancel each other out. Well, instead of using the addition property of equality here, we're going to use the division property of equality, and I'm going to take this equation where the exponent is higher, and I'm going to divide it by this equation where the exponent is somewhat lower, right? So this is the way that's going to look. A times b to the 5th equals 121.5, and I'm going to divide that by a times b to the 2nd is equal to 36. So I'm just taking the 2 equations, instead of adding them together or subtracting them or anything like that, I'm actually dividing them, because equals divided by equals are equal. Now what's great about that is that the a's cancel each other out, because a divided by a is simply equal to 1. All right, you've definitely canceled out factors that show up in the numerator and denominator before. But now I have b to the 5th divided by b to the 2nd, so that's just b to the 3rd. And I'm going to, for the time being, just leave this like this. I'm not going to even worry about what 121.5 divided by 36 is. I'm just going to leave it like that. Let me make the decimal look a little bit bigger. This technique will always work 100% of the time. All right? Now, because we've eliminated the a by division, we can now solve for b in, ironically, part C, letter C. Solve the resulting equation from b for the base b. All right, well, I've got b cubed equals 121.5 divided by 36. B will simply be the cubed root of this ratio, or this ratio raised to the 1/3 power. All right, so b is either equal to the cubed root of 121.5 divided by 36, or b is equal to 121.5 divided by 36 to the 1/3. Again, I kind of like the 1/3 power only because you've already seen I sort of struggle a little bit kind of getting the general root in there. Anyway, I'm going to clear out my history. So what I'm going to do is I'm going to, I think, do this version of it. I'll put down a parentheses, have my fraction. I have 121.5 divided by 36. And I'm going to raise all of that to the 1/3 power. And again, perfectly okay to simply use the cubed root if you like that better. So when I find the 1/3 power of this ratio, it ends up giving me a b value that's very nice. I made it nice in this problem. And sorry, let me just do this. b is equal to 1.5. All right. Now, what's interesting is in all the other problems, we knew the value of a, and we used it to find the value of b. Now we know the value of b, and we don't know the value of a, but let's figure out how to find it in letter D. This is killing me with all these subparts that have letter names. Anyway, letter D. Use your value from C to determine the value of a. State the final equation. All right, well, how do we do that? The beautiful thing is, we can now take this value of b, we can substitute it into either one of these two equations, whichever one you like, and it doesn't matter, and we can use that to find the value of a. I'm going to substitute it into the first equation because it's the first equation, numbers are smaller, all that kind of stuff. So what I'm going to now do is I'm going to say 36 is equal to a times 1.5 squared. Now, no matter how simple or complicated the value of b is, me personally, I will never try to figure out what this quantity is squared or cubed or whatever it is. What I will now immediately do is just simply divide both sides by whatever this thing is. I'll let my calculator do that entire calculation on its own. Right? There's no reason for me to figure out what 1.5 squared is and write out decimals, and at least that one wouldn't be terrible, because I can now just do 36 divided by 1.5 squared. And I'm going to get a equals 16. Let me just bring that back up for a moment. Now, most of the time, by the way, b is going to be rather ugly. The base is going to be kind of an ugly thing, and we're going to not want to round anything before we come up with the value of a based on b. Because as soon as we round b and use it to find the value of a, then both b is a little bit off and a can be remarkably off depending on how much you've rounded b. All right? So again, here in this stage, I'm never going to figure out what that kind of quantity is. I'm just going to divide through by it and figure out a. And now I've got my final equation. State my final equation. Let's do it. Full screen. I now know f of x is equal to 16 times 1.5 raised to the x. And that is it. That procedure, literally substitute the two given points into the general form of the exponential equation, divide the two equations to eliminate a, subtract powers of b, then use some kind of a root to figure out the value of b, substitute b back in to find the value of a, will work every time to find the equation of an exponential given that you have 2 points that lie on that exponential. Not 4, but 2. All right, so a fluency expectation. All right, every single math course that you go into, there's what are called fluency expectations, meaning skills that they want you to be so good at that you're fluent at them. You can just kind of roll right through them. It's a fluency expectation that you can form the equation of any exponential function given any two input-output pairs. Sometimes these pairs will be given graphically. So let's take a look at exercise number 5. Find the equation of the exponential function shown graphed below. Be careful in terms of your exponent manipulation. State your final answer in the form a times b to the x. All right. Now notice, this is a decreasing exponential, so right away we know that the value of b is going to be between 0 and 1. All right. We also know that the value of a is going to be between 0.5 and 128, but that's not particularly helpful. All right. Pause the video now and see if you can go through what we just did to come up with the equation of this exponential. And then obviously we'll walk through it nice and slowly. All right, let's do it. So let me write down the 2 points so that you can see them a little bit larger. I've got -2, 128, and 2, 0.5. All right, so first things first, what I'm going to do is I'm going to substitute these points into that general form. So on the first one, I've got 128 is equal to a times b to the -2. And in the second one, I have 0.5 is equal to a times b to the +2. Okay, great. And that's always our first step. Now, as a second step, what I want to do is divide these two equations. It doesn't matter which order you divide them in because either way the a's are going to cancel. But I tend to like to always divide them so that the higher power, which is positive 2, is in the numerator and the lower power, which is negative 2, is in the denominator. So this is the way I would do the division personally. I'm going to just do this. I'm going to say a times b to the second is equal to 0.5 divided by a times b to the minus 2 is equal to 128. Now again, don't let that 0.5 divided by 128 scare you. I'm never going to figure out what this ratio is. It's an ugly decimal. I don't care what it is. All right. I'm going to cancel these. Now here's where we have to be very careful. Remember, b to the second divided by b to the minus 2, right, is going to be b to the 2 minus negative 2, which is going to be b to the fourth. All right, b to the fourth, not b to the 0. If it was b to the 0, we'd be in trouble because b to the 0 is equal to 1, and then we couldn't figure out what b was. Anyhow, regardless, right, we end up getting b to the fourth is equal to 0.5 divided by 128, which means b must be 0.5 divided by 128 to the 1/4, or the fourth root. All right, let me bail out of here and just kind of come into here, bring this over. Let me just clear this out so we've got it nice and clear. Put my fraction in, 0.5 divided by 128, raised to the 1/4, enter. Right? We have a beautiful base. Again, my bases are going to get ugly in just a moment, but here I've got a base of 0.25 or 1/4. Let me just move that, write this down. 0.25 is my base. I'm going to go back into full screen really quick. Once I've got that base, what I can then do is use the base along with either one of these two equations to figure out the value of a. I personally think that this is an easier equation to work with. The 0.5 equals a times b to the second. So that's what I'm going to now do. I'm going to say 0.5 is equal to a times, 0.5 is equal to a times 0.25 to the second. Man, keep needing more page here. So a now is going to be 0.5 divided by 0.25 squared. And that, let's take a look, 0.5 divided by 0.25 squared gives me an a value equal to 8. A is equal to 8. So finally, right, we can now say that our final equation is y equals 8 times 0.25 to the x. And there we have it. Now, as a side note, because both the 8 and the 0.25 were nice numbers, we didn't round either one of them, they were perfectly good. You could now use this thing, you could substitute it into your calculator if you wanted to, and you could easily check to see if it's correct, right? Or you could just check these 2 points. You could take x equals 2, substitute it into the equation, make sure you get 128, substitute x equals positive 2 into the equation, make sure you get 0.5. All right, that's easy to check. Unlike, I think it was exercise 2 or 3, I think it was exercise 3, where we had to round the value of b, so our check resulted in something that wasn't quite right. All right, let's do one more where things are a little bit messier. Exercise number 6. A bacterial colony is growing at an exponential rate. It is known that after 4 hours, its population is at 98 bacteria, and after 9 hours, it is at 189 bacteria. Determine an equation in y equals a times b to the x form that models the population y as a function of the number of hours x. Round b to the nearest hundredth. At what % rate is the population growing per hour? All right, so there's a lot going on here. What I'd like you to do is pause the video now and see if you can come up with this model. All right, let's write down our 2 points. All right, they told us that after 4 hours, there are 98 bacteria present, and after 9 hours, there are 189 bacteria present. We're going to substitute those 2 points into this particular form of the equation. So I'm going to get 98 is equal to a times b to the 4th, and 189 is equal to a times b to the 9th. I'm now going to take those two and I'm going to divide them. So I'm going to have a times b to the 9th is equal to 189 divided by a times b to the 4th is equal to 98. This one's a little bit easier, no negative exponents, so I'm just going to do that. I can then cancel that and be left with b to the 5th is equal to 189 divided by 98. So b is going to be 189 divided by 98 to the 1/5. Okay, and again, let's talk about a little calculator technique here. All right. Bring my calculator out. Let me just clear my history out. 189 divided by 98 to the 1/5, all right, gives me a b value of of course it just disappeared, 1.1403, etc. Now, I know that the problem says round b to the nearest hundredth, and I will eventually, all right? I'll eventually round that to 1.14. But when I find the value of a, in order to keep a as accurate as possible, what I'd like to do is not use the rounded version of a to find, the rounded version of b to find the value of a. In fact, what I'd like to do is use this first equation, and again, either one of them works equally well, right? I can use this equation, let me do a little line out here. A is going to be equal to 98 divided by b, which is 1.1403, etc., raised to the 4th. All right, and the beautiful thing is that since we always will find a immediately after finding b, right? We found b, and we're going to find a immediately afterwards. Then what I can now do is I can literally just say, hey, calculator, tell me what 98 divided by my answer, I'm trying to find answer, what my answer to the 4th is. Okay, so just before I even hit enter here, right? Here is my answer for the value of b, unrounded in its terrible decimal glory. I then know that a is going to be 98 divided by b raised to the 4th, so I just say to my calculator, take 98 and divide it by my previous answer raised to the 4th. By doing that, I don't risk any kind of a rounding error that like throws me off. And again, here, right, I find that A, which remember is the starting bacteria population, is 57.94, etc. You might say that they didn't tell you what to round A to, but A is the starting value for the number of bacteria we have. So we're going to round A to 58, right? We can't have a fraction of bacteria. If we had used just the 1.14, now it's 1.140, so that's not terrible. But if it had been like 1.144, and we had rounded and used 1.14, we might get a very different value for A. Well, maybe not a very different value, but a somewhat different value. So let's write down our final model now. We've got everything we need. So we can now say y is equal to 58 times 1.14 raised to the x. There's one little last piece of this, and we're going to get into this a lot in coming lessons, which is what is the percent population, at what percent rate is the population growing per hour? Pause the video for a moment and see if you can dig out some knowledge that you had from Algebra 1 that tells you how to look at this and say what percent the population is growing at. Pause the video now. All right, now don't worry too much if this is buried too deeply, okay? I just wanted to give a preview of what's coming. Literally, this number here in front of the 1 tells us that it's growing at a rate of 14% per hour. And again, we're going to spend an entire lesson just looking at exponential models that are based on percent growth and decay. So if that's a little bit too buried for you, I wouldn't be too worried about it right at this moment. All right, let's wrap this up. You spent a lot of time over the years coming up with equations of lines if you knew 2 points that lied on the line. And think about how you always did that. Typically, you'd find the slope of the line, you'd substitute the slope of the line back into y equals mx plus b, and then you'd use one of the 2 points to figure out what the value of b is. That's very similar to what we did today, except instead of finding the equation of a line, we found the equation of an exponential. Now, in general, the way that you do that, the most general way, is take the 2 points that you're given, substitute them both into the general form of the exponential equation. That will result in a system of equations that has both the a and the b values of our exponential model in them. Dividing those 2 equations will always eliminate the a variable and allow you to figure out what the value of the base is. Once you know the value of the base, you can then substitute that back into the equation to figure out the value of the a, which is the y-intercept of the model. This is an exceptionally important sort of technique to learn right now because we're going to be using it in a lot of lessons that are coming up in this unit and in the next unit. So anyway, try to really understand it and get fluency with this technique. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.